to some components or some kind of flow discontinuities in the piping system. So we discussed the minor losses due to entrance, then sudden contraction, sudden expansion, then flow through a pipe into a reservoir, and then the losses in different type of valves, then bands, T joint, and then uh, similar components. So, and then in the last portion of the class, we did two numericals. Now, in whenever we do the analysis of piping system, there are three types of problem which we face in terms of analysis. In first type of analysis, we need to determine either the pressure drop or head loss in the piping system. In the second problem, we need to determine the flow rate through the piping system. And then in the third type of problem, we need to determine the diameter of pipe which should be used for the piping system for the given flow condition. So these first two types of problem are quite straightforward, and we will do some of couple of numericals for each. But the third one, it is quite laborious or quite cumbersome analysis, because everything in the piping system depends upon the diameter of the pipe. Why is that? Because if we want to calculate Reynolds number, that depends upon the piping system. Then if we want to calculate the flow rate or velocity, that is always a function of diameter Q upon A. And then if we want to calculate major losses, we also know that is dependent upon diameter. So it means that if the diameter is unknown, then it's kind of repetitive analysis. It means that we need to guess the value of diameter and then conduct the analysis, and in the end we need to compare the value which we get from the analysis with the initial assumed value. If it is correct, then it means that our analysis was correct. Otherwise, we need to make some kind of correction in that initial guess. And so it is kind of iterative process. So first of all, we would do some numerical examples for the pressure drop or head loss calculation, and then the second type, and in the last we would do some problems related with the diameter determination for the piping system. So in the last class, if you remember, that we did these two problems. So I hope that these two problems are clear to you. So now, as I discussed, that for the pipe flow analysis, we have got three types of problem. In the first problem, we need to determine pressure drop or head loss, and in all other parameters are known to us. Then in the second type of problem, we need to determine flow rate or average velocity. So, and all other parameters are given. And in the third type of problem, we need to determine diameter of the pipe, which is required to satisfy all other flow conditions. So this type 3 problems, they cannot be done in a single go. So that's why we need to have some kind of iterative method. So we will discuss that later. But in today's class, we will try to cover these two types of flow analysis. And the first type, where we need to determine pressure drop, and in the second type we need to determine the flow rate. Okay, so first of all, we do pressure drop determination problem. So this is a case where the flow is happening from overhead tank. So the pressure at section 2. So section 2 is at this point, which is at the end of the piping system. It is not allowed to fall below 60 psi, pound force per square inch. So its value shouldn't be less than that, because normally when there is a low pressure in piping system, then there is a phenomena of cavitation. So we need to avoid cavitation phenomena in piping system in order to suppress the vibration which would occur if there is uh, some kind of cavitation. So when the flow rate of water, whose kinematic viscosity and specific gravity value is given, from the tank varies from 0 to 1 cubic feet per second. CFS means cubic feet per second. And the branch line is shut off. So this branch line here, which is shown in the piping system, that is shut off. Determine the minimum height edge of the water tank. We are talking about this height, which is this, which is shown here. Under the assumption that minor losses are negligible. So in the first scenario, we need to neglect the minor losses, and in the second part, we need to include the minor losses. So first of all, I think it is better that if we can copy this figure on the whiteboard so that it is in front of us. So let me do that. So if we take it, okay, and then so this is a problem schematic. So now, first of all, in these problems, in the first part, because there are no minor losses, so we can write the energy equation between point 1, which is here, and point 1 is here, and point 2 is this is 1 and 2. So if we write the energy equation here, we can write P1 upon gamma plus V1 square upon 2G plus Z1 is equal to P2 upon gamma plus V2 square upon 2G plus Z2 plus FL upon D V square upon 2G. So this is our equation. So now the P1 value, which is at point 1 here, because if we talk about the gauge pressure, then it would be P1 would be equal to 0. V1, that would also be equal to 0. Why is that? Because it is a large tank, so the velocity at the free surface would be equal to 0. Okay, and Z1, if we take this as a reference point for the height, then we can say that Z1 would be equal to 6 plus H plus 10. So Z1 would be equal to 16 plus H. Okay, now coming to the pressure at P2. So because we know that the P2 needs to be less it should be equal to 60 psi. It shouldn't be less than that. So we are going to design on that. So 60 psi, and V2 value Okay, so we would design it at the maximum flow rate. Why is that? Because at the maximum flow rate, the dynamic head is maximum and static head would be minimum. So it means that V2 velocity we would take one cubic feet per second, right? And then Z2 would be equal to 0 because that is the datum point, and then F we don't know. Okay, what is the length here? It would be, if you see here, that it is 600 feet of straight 5, then 600 feet with 1.1590 degree elbow. So elbows would come in the minor losses, which we are neglecting at the moment. So 600 feet plus 900 feet, 1500, 1500 plus 6 plus 10. So it would be, L would be, total length of the pipe would be equal to 1516 plus H. Right, diameter of the pipe, it is given as 6-inch diameter plastic pipe. Epsilon upon D is equal to 0, and it is flange fitting, right? So we are talking about flange fitting here. So first of all, what we do, that we just try to find the value of V2. So V2 would be equal to V2 would be equal to V, that would be equal to Q upon A, right? So Q value, that is 1 cubic feet per minute. So we just write it 1 cubic feet, 1 cubic feet per second, CFS, divided by area. Now, because area would be equal to pi by 4 into diameter. So diameter should be in feet. So 6 inches would be 6 by 12, right? So V2 comes out to be 5.09 feet per second, right? So now we know that V1 is equal to 0. So that would be equal to 0. And then P1, that is in terms of gauge pressure, that is also equal to 0. And then Z2 is equal to 0, right? So in this equation, if we put the values now, so it would be 16 plus H, which is Z1, is equal to P2 upon gamma. So P2 value is 60 pound per square inch, so pound force. So we need to deal in a pound force per feet. So it means that we need to multiply it with 144 to convert the per inch square into per feet square. And gamma value, it is given in the statement, that is 62.4 pound per feet square. Okay, and then we have got these two terms, which is it can be 1 plus F L upon D V square upon 2G. So V square in this case, that is 5.09 square divided by 2G, 2 into 32.2, that is the gravitational constant. So now we need to and what is length here? We can write length straight away. So that length is 1516 plus 1516 plus H, right? That is the total length of the pipe. So which would that F calculation that needs to be done here. So epsilon upon D is equal to 0 in this case, and then we need to calculate the Reynolds number. So Reynolds number would be equal to rho Vd, or we can just write it velocity into diameter divided by kinematic viscosity. So kinematic viscosity value is given in the statement, that is 1.2 into 10 to power raised to minus 6, and velocity, that is 5.09, diameter 6 by 12. So if we put in the values, we can see that that is equal to 2.10 into 10 to the power 5, and then epsilon upon d value is equal to 0. So now we would either use Moody chart or okay. So either we can use this. So the last bottom curve here, that is for the epsilon upon d is equal to 0. So from here, if 2 into 10 to the power 5 we are talking about, so that would be somewhere 2 into 10 to the power 5. It would be around 0.0155, or we can also use either of these two relations to get the value of friction factor. So let me take you back to the problem. So here, if we, as I have shown you on the Moody chart, that comes out to be 0.0155. So this value can be calculated from the Moody chart or Colebrook relation, which are on the next slide. So once we get this, now it is just a matter of putting the friction value, diameter value, and then take h, the terms involving h on the left hand side and other on the right hand side. So if we do the calculation, h value, that is the head which is needed here to make sure that the pressure doesn't drop below 60 psi at the maximum volumetric flow rate of 1 cubic feet per second. That comes out to be 143 feet. So this overhead tank, it is usually installed in many of the societies, housing societies. We normally see that the water comes from a main storage tank. So it is kind of that. It is the design of that overhead storage. So this was the part one, which was when we have got no minor loss. And now we need to consider the minor loss in part B. So for that, if we write the equation now, the equation would be almost the same, but there would be one additional term, P2 upon gamma plus P2 square upon 2G plus Z2 plus Fl upon D V square upon 2G plus Kl V square upon 2G. Now this is the minor loss term. This is the minor loss term. So we need to calculate summation of Kl. Now if we see the this piping system, so there are kind of one loss when the flow enters from this overhead tank into the piping system. So that is, if we take it sharp edge entrance, so KL value is 0.5 for this case. Then we have got 1590-degree elbow. So 90-degree elbow. So if we see here the part A of this table, we have got 90-degree elbows. Now there are two types of elbows. One is flanged and one is threaded. So as you see that they haven't mentioned, so you are free to take any of these two, either flanged or threaded. But if you look closely, that they have mentioned here that pipe is 6-inch diameter plastic, epsilon upon d is equal to 0, and all the fittings are flanged. So it means that we need to take KL value for the flanged elbow. So that is 0.3, right? So there are I think 15 elbows. So it means that if we start writing KL value here, okay, so I will write it here. KL would be equal to 0.5. That is for the entrance, the flow which is sharp sharp edge entrance in which the flow enters from the reservoir into pipe, as we discussed in the minor laws. If I take you back here, this is the sharp edge. So for the part B, if you see, that is 0.5. KL is equal to 0.5. So one thing we have taken that. Okay, and then KL 0.5 plus 15 90-degree elbow, so 15 into 0.3. Okay, any other component? There is a kind of T here, branch line. So even it is closed, but there is a component. So it means that we need to also consider that. So for the T, if we look that K value is for the T flanged one, its value is 0.2. Where the mouse cursor is. I hope that you can see it, but it is in the table. So T's are here. So flanked T would have been KL value 0.2. So we just write it here 0.2, and then from here KL total value becomes equal to 5.2. So now if we go back here, KL value is known and all other values are known, so we just put in the values. So H value comes out to be 146 feet when we include the minor loss. Without minor loss, with minor loss. So if you see that for this problem, because the straight pipe length is more than 1500, so it means that obviously the the majority of the loss would be from the friction in the straight pipe, because there are 1500 feet of more than 1500 feet of straight pipe. So that's why the majority of the loss is due to viscous frictional effects, and because there are only a few components like 16 17 components, so the loss incurred in due to those components, that is a little bit less. So it means that even if we neglect the minor losses, the calculation would have been acceptable, but it is better to include it just for the make sure just to make sure that we are not losing any important parameters. So it is, so we are going to it was just to show that what is the difference when we do the analysis uh, with minor losses and without minor losses. So if there is any query, you can ask. Otherwise, we can start with the next problem. Okay, so everything is fine. So that's good. So now the next problem is that we have water is flowing through the coils of the heat exchanger. Now, one thing which is I would talk it maybe in a couple of minutes. So water flows through the coils of the heat exchanger. Epsilon upon D value is given 1.2 into 10 to the power minus 4, and it is flowing at a rate of 0.9 gallons per minute. So 1 gallon is equal to 0.1336 feet cube. Determine the pressure drop between the inlet and outlet of the horizontal device or the heat exchanger. So, okay, so first of all, as we did in for the last one, we are going to copy it. So Okay, so this is the schematic. So now we will write the energy equation for this. That is the same thing as we discussed. So that is, if I start right, okay. Okay, so it would be P1 upon gamma plus V1 square upon 2G plus Z1 is equal to P2 upon gamma plus V2 square upon 2G plus Z2 plus FL upon D V square upon 2G plus summation KL V square upon 2G. Right. So this is the equation. So now we start seeing that what are all these variables. First of all, we need to determine P1 minus P2. So there is nothing to be written for pressure, because that is the thing, pressure difference we need to find. Then, because the diameter of the pipe is the same, so V1 is equal to V2 is equal to V, and that is we need to determine. So that is Q upon A. So Q value, that would be, if we see the statement, that was 0.9 gallon per minute. So 0.9 into 1.1336, zero point 0.9 to convert into feet cube per second, 0.1336 divided by cross-sectional area, that is pi by 4, into diameter is zero point 0.5 inches. So 0.5 inches, so we need to convert into feet. So that would be a point. So if we see the value of velocity comes out to be equal to 1.47 1.47 feet per second. Right. So velocity is known. Now, what is the Z1 and Z2? Because at the moment it looks like that flow is happening from the top to the bottom, but because there is no mention of height difference, so it is highly possible that this is a kind of a top view of the heat exchanger rather than the front view. Because if we look at the from the front side, it looks like there is an elevation difference. But if we consider it a top view, so it means that it is most likely that the this figure is taken uh, uh, from the top. So it means that Z1 is equal to Z2, and then we need to calculate this friction factor, and we also need to calculate Kn. Okay, so first of all, what is the length of the pipe? So length of the pipe, if we see 1, 2, 3, 4, 5, 6, 7, 8. So it means that length of the pipe would be equal to 18 divided by 12 into 8. So it would be equal to, I think, 12 feet, because 1.5 into 8, that would be equal to 12 feet. And now we need to calculate the value of friction factor. So for that we need Reynolds number, which is equal to V into D upon kinematic viscosity. Let me see that whether kinematic viscosity is given. So that's good. So is it kinematic viscosity? Yes, kinematic viscosity. So if we see that the Reynolds number comes out to be, if we put in the value velocity 1.47, diameter 0.5 divided by 12, and kinematic viscosity value is 1.66 into 10 to power raised to power minus 5. So if we put that value, uh, that uh, that value, Reynolds number 3690, and then we also know the epsilon upon d value, that is in the problem statement. If we see that value is 1.2 into 10 to the power minus 4, So then again, going into the Moody chart or by the use of Colebrook relation, we can find the value of F, as we have discussed it more than couple of times in the lecture. So that friction factor can be calculated from here, and then that comes out to be 0.041, right? So I would strongly suggest that you should use Colebrook relation. So I would give the relation in the paper. So all you need to do is to put in the value to find that friction factor, because from the Moody chart the problem is because the scale is in logarithmic, so it is quite difficult to see the exact value of friction factor, which is very important parameter. So I would strongly suggest using the Colebrook relation. So from here, friction factor is 0.041, and then once we get friction factor, now we need to calculate KL value. So if we see that there are 180-degree turns, so how many turns are there? One, two, let me, one, oh, okay. This is one, two, three, four, five, six, 7. Okay, 7 180-degree turns, and they are threaded, right? So threaded 180-degree turns. So if we go into the table again, uh, here the B, that B section, 180-degree flange and threaded. So for the threaded, it is 1.5 KL value. So 7 into 1.5. So summation of, okay, 7 into 1.5, which would be equal to, I think it would be equal to 10.5. So now we know all the values, right? Velocity, length, diameter. So we need to calculate P1 minus P2. So it is quite easy that we multiply the whole equation with gamma, and this Z1 and Z2, they would be cancelled out. So P1 minus P2, we multiply whole equation with gamma, and then we put in the values. So, and I can trust you on that you can put in all the values which we have determined. So P1 minus P2, that comes out to be 46.8 pound force per feet square, or if we want to write it in psi, that would be equal to 0.325 psi, right? So that was the calculation of pressure drop. So now we have discussed, uh, we can quickly do one more numerical for this. So up till now we have discussed the pressure drop determination. Now we move on to the second type of problem, which is flow rate determination. So in this, water flows from the nozzle adit to the spray tank, as shown in the figure. Determine the flow rate if the loss coefficient for the nozzle based on upstream condition. So the upstream condition, it means the velocity in this pipe is 0.75, downstream condition is 2, which is this. So, and the friction factor for the rough hose is 0.11, and gamma value is also given. So we need to, because it is quite a small problem, so it wouldn't take more than maybe 5 minutes. So let's do it quickly. So uh, let me just copy it here. So okay, so this is I copy it, and then we can. Okay, so now again writing the that energy equation. So that is kind of the first step we do in these kind of problems. So P1 upon gamma plus V1 square upon 2G plus Z1 is equal to P2 upon gamma plus V2 square upon 2G plus Z2 plus FL upon D V square upon 2G plus summation of KL V square upon 2G. So first of all, we need to see that what are these values. So P1 would be equal to, in this case, that would be equal to 0, because if you see that P1 location is this. So because this is a kind of gauge pressure when we talk about, so P1 would be equal to 0. Oh no, not 0, because if the value is given, it is not kind of that atmospheric pressure. So P1 is equal to 150 kilopascal. P2 is equal to 0 when we talk about the gauge pressure, because the flow is going out in the atmosphere. So P2 is equal to 0. Then V1 we can say that is equal to V1 can be equal to 0, because that is we can say that this is a large container. So V1 is equal to 0, and then we have got Z1 value. So Z1, if you see, that is 0.8 meter, and then Z2, that is because the length of the pipe is 1.9 meter, this slanted pipe. So Z2 would be equal to 1.9 into sine of 40. So Z2 would be equal to 1.22 meters. Now we need to write V2 value. V2 can be written in terms of this V value which is inside this pipe. So we can say first of all V is equal to Q upon A, right? And then we can also say that Q is equal to A2 V2, right? So if you see that the diameter values inside the pipe and at the exit of nozzle, they are given, so we can say that A area into velocity, that would be equal to A2 V2. Now what is this area? That is this pipe. And what is this area? That is exit of this, which is this, right? So from here we can calculate Q, and here if we put in the values, just a minute. So here I can write V2 is equal to, from this relation I can write Q upon A2, and then Q is also equal to A into V, so I can write it uh, A into V divided by A2, and then because the V is the velocity which is not known to us, so I think we can write it A upon A2 into V2. Now area, we know pi by 4 d square here, this area, and A2 would be pi by 4 into this pi by 4, 7.5 divided by 1000 square. So if we do that, it comes out to be 4 V, and that is obvious because that is double value. 15 mm is double as 7.5, so because that is square, so 15 divided by 7.52 into square 4 into V. V is the velocity, which is the flow velocity inside this pipe. So we know that, and now it's just a matter of putting the values. First of all, V1 is equal to 0. and then all other values, they are known. F value that is given to us, that is zero point 0.7, it is 0.11, and then KL value that is given to us 0.75. So let's put the values here. So I am going to show that step as well here. So P1 upon gamma, uh, it was 150 kilopascal. So let me write it, 150 into 10 to power 3 divided by gamma value. Gamma value is given to us in the statement, that is 9.8 into 10 to power 3. So I would write it here, 9.8 into 10 to power 3 plus V1, that is 0, V1 square upon 2G, plus Z1, which is zero point 0.8, and then we have got P2 upon gamma, that is also 0 because the flow is going out in the atmosphere. Then Z2, that is 1. No, V2 square, we can write it like this, that we can say V2 is equal to 4V. So we can write it 4V square upon 2G plus Z2 is 1.22 meter. I can put it here. F value, that is the friction factor value, that is that is zero point 0.1. Just a minute, zero point 0.1. It is 0.1 into what is the total length upon diameter. So length is 1.9 meter divided by diameter, that is I think 15 mm. So that would be equal to 0.015. Oh, 0.015 into V square upon 2G plus KL value, that is given to us 0.75 into V square upon 2G. So from here we can always get the value of V. So that comes out to be equal to 3.09. And then Q can be calculated area into V, and then we know area pi by 4 into 0.015 square into velocity 3.09. If we do that, put in the value, so it would be equal to 5.46 into 10 to power minus 4. I think this is meter cube per second. So by this we can, by this way we can find the velocity and the volume flow rate. So we did one numerical problem in this class. We will do one in the next class for the volume flow rate, and then the third type, which is pipe diameter determination, we will do it in the next class after lead. So if there is any question you can ask, otherwise we can just finish the lecture now.